We have spent the last several videos looking at various permutations of nucleophilic acyl substitution reactions of carboxylic acid derivatives. What we are going to look at now to kind of tie this all together is when we think about different carboxylic acid derivatives and their reactions in nucleophilic acyl substitution, are all of these carboxylic acid derivatives created equal, meaning they are all going to react equally well in nucleophilic acyl substitution, or do some react much more capably than others? Let's take a look at this, reviewing first the different carboxylic acid derivatives that we have in our lineup. In our lineup of carboxylic acid derivatives that we have focused on in this chapter, we have the acyl halides, which had a carbonyl group that was directly bonded to a halogen here. So X was a halogen in our so-called acyl halide. We also had acid anhydrides, which had a carbonyl group directly bonded to an oxygen, and that oxygen was bonded to a second carbonyl group that had another R group on there. We called that an anhydride, or a so-called acid anhydride. We also looked at esters, where esters had a carbonyl group directly bonded to an oxygen, and that oxygen was bonded to another alkyl group. So R prime was an alkyl group, and this made these molecules referred to as ester functional groups. We additionally focused in this chapter on amides, where we had a carbonyl group directly bonded to a nitrogen, and that nitrogen had two R groups bonded to a alkyl R prime, where R prime in this case could be a hydrogens or carbons, and that made these referred to as amide functional groups. So as we think about these different functional groups as examples here, if we were to react each of these in a nucleophilic acyl substitution reaction, what we would find in terms of their relative capabilities for nucleophilic acyl substitution is that if we were looking at the rate of reaction, what we would find is that the acyl halide would react the fastest in nucleophilic acyl substitution, whereas the amide would react the slowest, with the acid anhydride and the ester in between in order here, with acyl halide fastest, second fastest acid anhydride, third fastest ester, and last place the amide. So why is it the case that there is this vast difference in reactivity, where if we were to mix an acyl halide with water as our nucleophile, it would react in the course of minutes or possibly even less, and actually catalyst is not even required for that reaction. Whereas if we were reacting an amide with water, it would take literally centuries to react without the presence of a catalyst. So why is that the case that the acyl halides react so much faster and so much more readily than amides, when in each case they all have this carbonyl group and they are all bonded to a leaving group? The difference between them is what is the structure of the leaving group. So I've highlighted the leaving group in red in each of these cases. And that's what we can use to distinguish between these carboxylic acid derivatives. So we can infer, based on an observation that acyl halides react the fastest, amides react the slowest, that what must be going on here and creating that difference in reactivity is the nature of the leaving group having a major impact on the reaction rate. So the reason why we see this difference in reaction rate and can relate it to the structures of these leaving groups is that when we think about the nucleophilic acyl substitution reaction in general, what's happening in the reaction, as we've looked at in these anionic or basic nucleophile reactions so far, is that we have our carboxylic acid derivative, which could be any of those functional groups that we see at the top there. We react it with a basic nucleophile. So I'm putting a negatively charged nucleophile in there. And what happens during the reaction is that the leaving group, that is whatever group we've highlighted in red up top here, LV, is replaced with the nucleophile. So the nucleophile comes in, displaces the leaving group, which leaves as that leaving group anion. And so what is going to favor and promote this reaction is that the more stable this product is, the more stable that leaving group anion product, the more readily the reaction will occur, the more favorable the reaction will be. And so when we compare the leaving groups for an acyl halide versus an amide, we see definite differences there. In the case of the acyl halide, our leaving group halogen leaves as a halide anion. With our acid anhydride, when we break that away, we're going to have an oxygen directly bonded to a carbonyl, directly bonded to an R group, with a negative charge on that oxygen, because we've broken this oxygen carbon bond here of the leaving group to send that half of the molecule on its way. With our ester, we have an O alkyl group with a negative charge on the oxygen. And with the amide, we have NR2, where those R groups could be either hydrogens or carbons. And remember, the nitrogen had a lone pair of electrons on it to start with. When we break the covalent bond, it gets a second set of lone pair electrons, and it's going to have a negative formal charge. And so, keeping in mind that this nucleophilic acyl substitution reaction is going to be favored by the creation of a product that is stable, meaning a stable anionic leaving group, we look up here and we go, okay, this order of reactivity exactly parallels the stability of these different leaving groups, where a halogen anion is going to be the most stable of these four leaving groups on the product side, because the halogen is the most electronegative of those four. On the other end of the spectrum, the nitrogen is the least stable, and the reason the nitrogen is the least stable is because it is the least electronegative of the four types of atoms that can act as the leaving group. So halogen here has the greatest electronegativity, and the nitrogen, which is carrying the negative charge over here, has the lowest electronegativity. It is the least able to carry that negative formal charge and remain relatively stable, whereas halogens are super able to carry a negative formal charge, hence the reason that sodium chloride, salt, is stable sitting on your kitchen table. In the middle here, we have our two oxygen anions, and the oxygen anions are more stable than nitrogen because of the fact that oxygen has greater electronegativity. And the reason why the acid anhydride is going to be a more stable oxygen anion than the oxygen anion in the ester is because of the fact that the oxygen anion here in the acid anhydride is stabilized by resonance, because we could share that negative charge over both of these two oxygens, and that's going to create a situation where the oxygen anion is more stabilized than over here with the ester, where the negative formal charge is trapped just on the oxygen atom. So the reason why this leaving group from the acid anhydride is more stable than the O alkyl group from the ester is because of resonance, which delocalizes or shares the negative formal charge over multiple atoms. So we have to think there about the resonance that's going on and ask ourselves, is that resonance productive and stabilizing the molecule? And yes, it is in this case, because the negative charge is shared over multiple atoms. The negative charge isn't stuck on just this atom. The additional resonance structure we could draw would allow us to show that that negative charge is shared over both of those atoms. And so that's going to account for the extra stability of the acid anhydride relative to the ester. Still, the acid anhydride is inferior to the acyl halide because the halogen has so much larger electronegativity than the oxygen atom that the halogen atom is still going to win in terms of being able to carry that negative formal charge and remain relatively stable. And so therefore, when we're thinking about breaking away the leaving group, we are going to most favorably break away a halogen leaving group because that's going to give the most stable product as a result of these reactions. On the other hand, the amide functional group, the nitrogen, is the least capable of leaving because it's going to give a very unstable, negatively charged nitrogen, which is unstable relative to the oxygen or the halogen atoms of the others. And that's why when we're looking at the reduction reactions in the last video, we saw that in the reduction of the amides, that the nitrogen atom didn't actually break away in that reaction because the nitrogen is such an unstable leaving group that it's harder to reduce this under under basic conditions, and the nitrogen, in fact, is not going to break away during the course of that reduction reaction. So as we look at carboxylic acid derivatives and we aim to make specific products out of those, we can keep these principles in mind as we think about what starting materials are most favorable to use for reactions, where if we have an acyl halide on hand that we can use as a starting material for a nucleophilic acyl substitution reaction, that may be desirable over using one of these less reactive carboxylic acid derivatives. So we're organizing these in order from most reactive to least reactive carboxylic acid derivative here.